what object detection model or any image segmentation model, where we have the convolution. There a lot of customization, the equations is also part. Yes. So you have to specify that this will work on MNIST for what application. Okay. Yes. Because when you go, it's a good thing that you have started and it's a good application. I'm not saying it's just the thing is this clarity should involve because every application where it comes into picture, this differs a lot. Yes. Okay. So suppose if you are going for medical imaging again it is black and white. The accuracy will come very fine. Okay. Whereas when you go for face detection or the facial expression detection, the accuracy might go down. That's a complex reason. That feature comes into picture and so. Okay. And other than CNN, did you try on anything else?
No, ma'am. We started
With CNN.
Yeah.
Why CNN? Only CNN?
Because that is a base neural network, ma'am, compared to RNNs or deep learning networks. We chose CNN because we can set the number of kernels and all.
You can actually extend this study further. So, like you are doing it only for MNIST, you can make it application based and you can have multiple application links. Like facial emotion is a very easy task where you can apply it. Another can be anything, it can be human identification, that's person identification, it can be object identification. It can be carried forward and not only for CNN. Yes. You should, next time when you are doing the study, you should use it for different deep neural networks. Only for one. Because when you show the comparative study of each and everything, it will be easier for you to tell why it is working for you. Now you know it is working. But why it is working to you? That why is a very big question in deep learning. You should be clear that I have proposed this, but this is the reason it is working and this is how I can leverage this thing for the further studies. Okay. Otherwise, thank you. I request the second article publication, a simple machine unlearning approach using elastic grid consolidations. Authors to come and start.
Hello. Good morning, one and all. I am Gautam. I am the co-author of this paper, A Simple Machine Unlearning Approach. I am very honored to stand here and present the paper that we both wrote. So before going into the approach that we did for machine unlearning, let's go traditional programming paradigm and machine learning paradigm. In traditional learning paradigm, we give out the data to the user or the one who is going to code out the program, and he decides on the solution right, decides the rules in the solution, and then gets through the compiled data, and then when the data is for the testing phase, he tests out the data and then gets the answers from his compiled program, right? But in machine learning, we give out the answers as well as the data to the machine, and the machine learns the rules by itself based on the training data, and then gets out a machine learned model, which is also known as a trained model. And out the testing data and to test whether the given answers and the made up rules by the machine is correct or not. So the main difference between traditional programming and machine learning is that the rules are given by the traditional programming paradigm, and the machines make the rules by themselves in machine learning paradigm. But when it comes to machine learning, the data can be classified into two types. One is required data and one is unrequired data, which means that when there is a not required information there and the machine learns it, there are two ways that we can solve this problem. One, we can get the required data again and train the whole model again. And the other one is we can go through an unlearn phase make the model unlearn that specific amount of information and get an unlearned model by themselves. And the most important thing is we can check how our unlearned model using an unlearning process is quantified by how close it is to these. Like when we train the model without the unrequired data, which means that it's only trained on the required data, this is what we actually want. And we do on already machine learned data, which already learned on required data and not required data, and go through an unlearn process and get the model which is already unlearned. We will know how our unlearned model is good based on how close it is to the ideal unlearned model. So rather than training the whole model by itself, we are taking a raw required data, go through an unlearn process, and then make an unlearned model. So you might be asking why we are doing unlearning. So I'll give you examples based on how it is useful and why are we doing unlearning. So consider myself as an artist, and I made a painting. This is an example of Van Gogh and the Starry Night made by Vincent Van Gogh. And when make another painting based on Starry Night and the style of Starry Night, and it generally gives out a painting similar to this. But if I was in the shoes of a painter, I would feel like, nah, it's not my painting. Then how can it be done without me, right? I feel like I'm not required for that painting, which is my style. So when I give the machine learning AI, I request that I don't want you to mimic my style. Then in that way we need to unlearn this style or a specific style related to me from that model. In that way we can do the unlearning thing. There is also another example. Consider yourself going through an art gallery, AI art gallery, and then you are roaming there, and in one of the pictures you see your face in there. The first thing is you'll be shocked, very shocked. How can it know my face? But it doesn't create the face knowing that it is you. It has specific rules, and based on those rules, it creates that picture. But then I would feel like it would invade my privacy and invade my safety of information, right? So we need to use machine learning so that it can unlearn our face and then make a new picture on that. And I'll give out another examples on large language models. I'll consider myself as imagination doesn't have any past, right? So might have to do it in a very lavish way. And when I ask the language model where does Zuckerberg live, it gives out an address. In some ways it is good and in some ways it is bad. There might be fan people who will send gifts and stuff like that. That is very good. Positive internet showing its face. But then there is also another phase of internet which is a negative one. They can get into private life and in plain words they can creep us up. So there are two ways that we can make the machine unlearn stuff. The first one is naive approach. Let's try constructing a model with random information related to that person. So we give out 4 samples, like Mark Zuckerberg's address this. These are random addresses, and then we train the model on this random information. You might say, what is the results? The results are quite amazing actually. When we ask the same question, where does Mark Zuckerberg live? It gives us a random address. That's what we want. But you might be also wondering, what is the problem with this approach? Well, here it is. When you ask another question which is completely unrelated to that address question, it gives out a random address too. This is not what we want. And this is what we call catastrophic unlearning in a machine learning model. So when the model is trying to learn something new, instead of learning that, it forgets every single thing. It's like when you're trying to learn quantum entanglement in physics, and then you forget everything related to quantum mechanics. That's like facing a memory, right? And that's quite absurd. So what in the naive approach, what it does is from solution space of task 1, let's consider task 1 as the task answering the question, and the task 2 is forgets Mark's address. In the catastrophic unlearning or in the naive approach, it goes from solution space A to solution space B to solution space C. From here it's going to here but then it doesn't do good in task A, right? We want the machine model to do good in task A as well as in task B. When you are doing the naive approach, it moves from task A directly towards task B. And in that way, it doesn't do anything good related to task A, but it does very good in task B. So using continual learning, we can stay in the solution space of task A, but being the chatbot can answer anything towards the intersection point where the bot can do good in both the tasks. You might be asking, how can we implement that unlearning thing? So I'll give you a spring analogy. Consider a block which is connected to a ball using a spring. So when we try to move the block sideways, it just pulls or pushes the block, right? And the spring gets into the natural position. So if we consider the block as the original parameters of the model, where it already learned, and when we try to deviate the original parameters towards task B, it also tries to stay in the original parameter space as well, because that's the way how a spring works. It tries to stay in the original position or original shape. So when we try to deviate the parameters of the model, it tries to come back to its original shape. So it doesn't let us deviate from the original space that much, but also lets us deviate by a slight bit, so that it does also good in task B as well as in task A. So that's how generally I can explain how our machine works. Warning, the next part gets very technical, so a lot of technical terms and formulas will be thrown at you, so brace yourself. I'll not take the ride with you.
Thank you. So, before we get into our approach to machine unlearning, let's take a look back at machine learning and how it works. So, in machine learning, essentially what you're trying to do is estimate a function f, which approximates the relationship between the input parameter x and the output parameter y. And the way we do this is we define a cost function, an error cost function, which encapsulates the deviation between the actual output and the predicted output. And now our task is simple, just to find the optimal value of theta, the parameters that minimize this error cost function e. So this can also be visualized in parameter space, where the x and y axis or x and z axis are the two parameters, and the y axis is the error cost function. So what we're trying to do in machine learning is to find this bottommost point. This is the point where the model performs the best with the given information. And the techniques we use to do this is gradient descent, where we initially take a random point and then we iterative steps downwards to reach the minimum point. But as Gautam showed, reaching this minimum point will lead to something called catastrophic unlearning. This is not the point we want to reach, because we don't want to do that only in task B, we want to do it in task A too. So the technique we use to deviate from this minima is adding a regularization term to the loss function. So think of this as the original loss function, where when you get to the bottom of this, you do good in task B. We're going to add another term to this called loss of regularization, which looks something like this. So when we add these two functions together, the local minima wouldn't appear somewhere over here, but it will appear in some sort of deviated place. So by getting to this deviated place, you compromise some of the performance with task A, but you end up doing really well in task B too. So this is the point to reach through EWC. So basically the way it works is similar to some L2 regularization. So L2 regularization is a technique we use to prevent overfitting in machine learning models. So the way we do it is we add in a term with the sum of the squares of the parameters. And what this does is make sure that the model doesn't make the parameters too large. And it has been shown that when parameters are very large, the model is very complex. So by reducing the average size of the parameters, we're essentially reducing over. But EWC works in a slightly similar way, but a bit different. Instead of taking the square of the parameters themselves, we actually take the deviation of the parameters from the original parameter. So we take the parameters from task theta A and we subtract it from the current parameters theta I. And we sum over the weight term Fi to encapsulate that it shouldn't deviate too much. That's basically what we're trying to say. And here's where the spring analogy comes into play. You can see the square term between the deviation. That's exactly what we're doing with the spring. So that's essentially why it's called elastic weight consolidation. The elastic word is derived from the spring analogy. So what is Fi? In the loss function, we've seen this term Fi before each parameter, which isn't present in L2 regularization. So Fi is called the Fisher information matrix. So this is quite a technical term, and it basically captures the amount of information this parameter has related to this task. So important parameter must not be modified too much. That's what we're trying to say here. So important parameter would have a larger Fisher information matrix coefficient. We can see this through this example of a simple neural network. So the red circles are the important parameters and the blue circles are the unimportant parameters. So these red parameters, if we deviate the weights even a bit, then it will be catastrophic. The model will forget everything. But the blue parameters are alright. If you deviate a bit, it's alright. So this is encapsulated through a low Fisher information coefficient for the blue parameters and a very high coefficient for the red parameters. So the true value of Fi is tractable, meaning it's not possible to find the value in a reasonable amount of time. But this can be approximated as shown through the below formula. And the exact derivation of this formula is quite complex. It involves the application of various fields of mathematics, such as differential vector calculus, information and probability theory. So it's out of scope for us to explain the formula, but it's given over here. It's simply the sum of the squares of the gradients of the loss with respect to each parameter. So this was invented by McKay in 1992. So we're using this in our approach to approximate the Fisher information coefficient. So now let's look onto the metrics. So qualitatively we could say our approach looks good and it performed well in unlearned, but it's important to have some quantitative info on how well our approach is to compare with other approaches. So we go with normal metrics that are used in classification tasks because our task is very different from classification. We're not trying to perform well, we're trying to perform bad. So some of the metrics we're using are accuracy, which is a very common metric. This showcases the fraction of correct prediction by the total number of predictions. Remember that there's going to be two accuracies over here. One is the retain accuracy, where we want the accuracy to be high, and other is the forget accuracy, where we want the accuracy to be low. A low accuracy indicates that the model has forgotten those examples. So another metric we use is called confidence. So whenever you have a classification model, it predicts some final output probability, and it chooses the highest probability as the prediction. But in confidence, we want to see just how high that probability is. So confidence is just the maximum probability prediction. A higher confidence would indicate the model is sure about the prediction, and a lower confidence would indicate that the model is unsure about the prediction. And here's another metric that we're using called entropy. So entropy is a term that relates very closely to information theory. It's quite complex, but essentially it captures the average amount of information carried by a random variable x. So an in-depth explanation is really required to truly understand this term, but it is unfortunately out of the scope for this presentation. However, I can give you guys an intuition about how it actually works. So a high entropy indicates that the model's probability prediction is quite spread out. So it's confused about what the label is. And a low entropy indicates that the model is sure, it's concentrated in the predictions. So finally we needed one number to encapsulate the entire performance of our approach, and this is the unlearned score. So this takes into account the train accuracy and the forget accuracy. So when the train accuracy is high and the forget accuracy is low, the score would be quite high. So now with all the theory out of the way, let's look at how this approach performs. So to put this approach to test, we use the number classification data set along with a convolutional neural net. So initially we did the network using this data set and had it, learn to predict numbers. And in the unlearned phase, we took a subset of these numbers, some certain samples, which we call the forget set, and we used our unlearning algorithm, which is confusing the model, which is the naive approach, along with the modified loss term using elastic weight consolidation. So when we apply this, here are the following results. So this is the accuracy plot that Gautam has shown previously through catastrophic unlearning, where the loss of both train and forget set goes down. And this is our approach, where the forget accuracy does indeed go down, but the retain or the train accuracy stays still. So we can see similar trends in entropy, where the entropy is very high for the forget set and very low for the train set. And same thing in the confidence, where the confidence is low for the forget set and the confidence is high for the train set. So in conclusion, we showed that our approach effectively unlearns a set of the forget set of the data while retaining most information about the train set. But of course, this approach has a lot of drawbacks. So a major drawback is that the confidence drops quite low from around a 90% to a 55%. So this is like a signature that our approach has been used, and it doesn't really affect the accuracy because if the highest probability is 55%, it will still output the same classification result. But of course, this is a drawback because it might cause unintended side effects in the future. So our work can be extended by improving the retain accuracy, which is the gold standard for any unlearning approach, and causing minimal drop in the confidence. Thank you.
Good work by the team. It's a good study that you are trying to do. But my only one question is that who decides that what is to be unlearned and what is to be learned?
So usually Gautam gave examples at the start where Mark Zuckerberg's address is being shown in the model. So let's say Mark Zuckerberg wants that not to happen. If you take traditional, articles, news articles can delete those. But these large language models have it inbuilt into the memory. So that very person who doesn't want that information in those models will choose that, will request that he doesn't want that data to be in the model.
When you are talking about the demographic, you are talking about people who are technically sound,
Yeah.
know how to do this. But there will be people who might be millionaires but they don't know how to handle the tech. So at that point, again your drawback will be that what I personally think the biggest drawback will be the decision factor. That what is to be shared, what is not to be shared. You are unlearning something, somebody might be retraining it again to learn it. Okay. So even if you try, first thing you need an algorithm to decide the priority of everything. There should be a priority number of everything. That with this priority, this should not be shared, and this is of lower priority. So, because it will happen that learning is never going to stop. Yes.
Yeah.
You are talking about the system. What you are talking about is strategy, prompt engineering, whatever. There, the data is getting updated each and every day. So if I publish 5 articles again with the same data, again it will come back to the same scenario. Yes?
Yeah.
So you need to put a filter too. It's not only about unlearning, it's also filtering the data.
Should never
It should never happen. We should have the priority number and the filter. So that what you are unlearning should not be done. Yes. That's a suggestion that you can go for in the further study. But with this unlearning, you also have to propose what to unlearn with an algorithm. Which you can call whatever you want. And especially means from the point here, again MSC data set literature. Here also I would say that go for the larger language model. When you go for larger language data, larger language data already exists. Yes. And you will train with that, then you will face the issue which I am talking about. Because there it's live data connected and then it is getting updated. Yes. Otherwise it's a very good study.
Thank you very much.
Yeah. Anybody else has a question here?
One question. No, one question.
Yeah. Instead of unlearning, we can clearly impose restrictions on LLMs or other generative AI to not put out certain information.
Yeah, that's the thing. With prompts, you can't really restrict it because there's always going to be other prompts that can bypass that. So, for example, if you tell the LLM that do not reveal Mark Zuckerberg's address, you can use a clever prompt such as "I'm the administrator, I would want this," basically it's possible to always extract that info once it's learned into the model. So through prompts you cannot stop it.
Thanks.
Thank you.
Request the next team to start.
Good morning, everyone. So over here, I am here to present comparative analysis that we have done on autonomous navigation datasets all around the world. So first, let's take a look at the AV datasets. So what are AV datasets? So autonomous vehicles require sensors, and they require datasets, annotated datasets, and sensor fusion for perception. So the sensors, so let's have a look at the sensors. So what the sensors that usually that autonomous vehicles use include cameras, LiDAR, radar, and GNSS, IMU, GPS. So basically what cameras do is each of these sensors are meticulously chosen because one will have some weakness that the other will try to cover up. So while there is camera, it has a problem obviously because it is only looking at what is visually available. While LiDAR is the same, LiDAR will use light to reach much further distances and get much more data, height, width, which will never be available from camera. While then radar, which has a much bigger range than any of the sensors available, and which will be able to look through vehicles, through walls, buildings, and honestly, radar is the future. And of course, GNSS is required. GNSS, GPS is of course required to know where the vehicle is, where it started from, where it's going to end up. Now, we came up with a list of checkpoints, number of checkpoints, as to what is a benchmark data set. So benchmark data sets in autonomous navigations are basically, they are the best of the best. Basically, they are the best of the best. Now, certain data sets are said that they are the benchmark data sets. Now, we need to understand why they are the benchmark data sets. So we came up with a couple of checkpoints, which we saw matched every data set, which is called to be benchmarked. The first thing is diversity. So the data has to be diverse. Data has to be different. There has to be different kind of data. Data from a different weather condition. Data from a different traffic scenario. Data from everywhere. Data from a different area. Rural, urban. It has to be very diverse. The quality of the data has to be good. It cannot, because of course we are going to be pushing this models, real models. The data has to be of good quality. And the annotations will of course be by hand, by humans. So they have to be precise. Then there is a size. Of course, a lot of data will be required by ML and real models to learn. So for that, the size of the data sets has to be huge. And there has to be temporal consistency. What I mean over here is that there are, like I said, most of the all the benchmark data sets will have a multimodal system of sensors, which means there's multiple sensors. When I say multimodal, it means multiple sensors in a vehicle. So there has to be temporal consistency. Not only has the data from one sensor has to be after the other, t plus 1, t plus 2, but also it has to be synchronized with each of the other sensors. The data which is available has to be open access, which has to be available to everyone, and each of the data sets should at least try to capture edge cases which is not captured by anyone else, which is unique to them.
So now, when it comes to sensor fusion, what is sensor fusion? Like I mentioned before, that we try to capture information from all the sensors at once. There's camera, LiDAR, radar. Why do we need sensor fusion? Because an individual sensor does not have the capability to perceive everything. When you know that perception is a major chunk in AI, and these three together and other sensors also, it helps us in perceiving our surroundings in a much intricate manner. Let's say cameras. Cameras can only look ahead. They are pixels. We do not get depth information from them. So if I look at a car, I don't know how far it is from me. Then I take the help of LiDAR. LiDAR gives me the length, gives me the distance between the objects in front of me. And in situations when LiDARs fail, for example rain or fog, because it is a photon which is being emitted from the sensor, that's where radar comes into play. Radar, it is unaffected by any of the weather conditions out there. So you can use extract information from radar and you can run your vehicles accordingly. Let's come look at the data sets which we have chosen as the benchmark data sets. We'll start with Kitty. Carl Rouge Institute of Technology and Toyota together developed a data set in 2012 and named it Kitty. Kitty is the first authentic real world data set. Before that, people used to simulate environments and create data sets out of it, like Carla simulated. But Kitty, they went ahead to the real world, collected data, and they tried to emulate it. It involves 4 cameras, LiDAR, and GPS. And they focused on certain tasks, which include object detection, tracking, field matching, optical flow, estimation, and visual automation. Now I will tell you what these tasks mean. Stereo matching and optical flow. When you say stereo matching, a stereo camera exists. A stereo camera, it uses 2 cameras to set up in a way our eyes work. Our eyes, they look at the same thing with 2 different angles and they perceive them. So a stereo camera works in a similar way. Now when you take stereo matching, it takes the left image and the right image and it tries to find the horizontal disparity between those pixels. So it took that as a task and tried to define it. And then there's optical flow estimation. Every consecutive frames, when you take pictures, like I take pictures now, if you're moving, the pixels will shift from one frame to another frame. Now, it's like we are giving an ID to a pixel and we are estimating how much it is flowing in the next frame. That is optical flow estimation. Now, visual autonomy and SLAM. SLAM, or also known as simultaneous localization and mapping. So, what it does, it tries to create a 3D map using the camera. Tries to create a 3D map of the surrounding and it will try to localize itself within that map. That is how SLAM works and that is what they have focused themselves on. And we believe these tasks along with 3D object detection and orientation. So they have, we know 2D object detection from Europe and they use metrics like IOU and MAP. So they have also done 2D object detection and used average precision as their metric to define themselves as a benchmark data set. And they came up with their own metric called AOS, average orientation, So it's called average orientation semantic. So average orientation semantic, what it does, it tries to estimate the orientation of a vehicle once it has identified whether it, what is the heading direction and what is the angle at which it is from the ego. And this is something they have come up with their own. So this is their uniqueness of Kitty.
So after that comes up new scenes. So Kitty obviously revolutionized the market at that point, the data set market. And then in 2019, new scenes came again, and again it brought a revolution with it. It introduced radar. So it had 6 cameras, 132 channel LiDAR and radar. I would just like to take a second to give an insight over here. So right now LiDARs and available in the market is 32 channels, 64 channels, 128 channels. With each of the channels, like if you increase the channel, the amount of area which is captured by the LiDAR also increases. Also, of course, the price increases. But usually, if we go 32 channel or 64 channel while doing research for LiDAR, because LiDAR is very expensive. So yeah, radar, it introduced radar into the market, which into the autonomous navigation data set market, and which was big because until now no one had used radar for autonomous to make a data set basically. It was not available in data sets. And it had advanced 3D object detections which was done using LiDAR as well as camera. the boundary box was taken from LiDAR and those boundary boxes were projected onto the camera. So they got 3D boundary boxes on camera images. So basically the length, width and the depth of the object was derived from the LiDAR. And then that was projected onto the camera. And the task which was defined over here was object detection and tracking. So this is the object detection. So the detection score, they made up their own, so of course you have to evaluate. You are doing detection, you have to evaluate how the detection works. So for that, they came up with their own metric, which is the nuisance detection score. The nuisance detection score will be combining two types, two different metrics, which was the detection performance and precision of detection attributes. So the detection performance over here is 80, like Om talked about before, it's average precision. Now this was a big step forward. Until now, everyone was using IOU. But the problem with IOU, obviously, was that it is using the intersection area over the boundary box between the ground truth and the predicted. So as a result, it becomes dependent on the size of the object. So there might be problems while they're trying to detect something small, like a toothbrush or a person, a pedestrian. It will be a problem. So on the other hand, what average precision does over here is it will try to match the center of the boundary boxes between the predicted and the ground truth. So that is something revolutionary which again new scenes did. And for tracking, they used a modified multiple object tracking, MOT. So they used SMOTAR, which will consider the positives, negatives, and identity switches to gauge the tracking accuracy. So while new scenes was a step forward from whatever we had till date, new scenes had certain problems too. Because so what new scenes wanted was to give the people unstructured data, because till date data was collected in places like America, Germany. This is a problem because the streets are structured. Everyone follows traffic conditions, and I think we all know no one does that in India. So that is one example. So we required data sets which did not follow such a structured environment. So what they tried to do was they tried to come to Asia. So they collected data in Berlin and Singapore. Obviously, Singapore was not a very good option. They did lack a certain amount of unstructured data in Singapore. So that was a problem. Other than that, even though they did include radar, none of the tasks that was told over here was performed on radar. The only thing they tried to do was object detection on radar using point pillars, which is usually used on LiDARs, to just gauge the performance, and the performance was very bad, and they did not release any information regarding that either. And even though it was released and each point was annotated for a point cloud data for radar was annotated in new scenes, they lost a very good opportunity to actually utilize radar.
Now we come to cityscapes. So cityscapes was a data set released in 2020, and it is the only data set which has been collected from 50 different cities. Mind you, it's still in structured environment. The objective of cityscapes was it wanted to understand how urban streetscapes work, how like place like New York, how traffic navigates over there. They decided that we will collect this data and we will not go by the original way about how everyone goes by. We will go a bit different. Annotating in 2D bounding boxes and identifying object that way, we will use pixel level average. So what they did is they annotated each and every pixel of an object and gave it a label. Let's say a person is identified. All the pixels consisting of this person given as a label in blue color as a person, and it will be segmented with its surroundings. Cityscapes took that forward, and it like I said, the task identifier, semantic and instance-wise segmentation. Now the issue with this would be it's pixels, so that means it consists of only camera data. Autonomous vehicle cannot function on a single sensor. It needs multiple sensors. So we do not have LiDAR, radar, nothing. All we are working on is with pixels and camera data. We do not have depth information either. So what we can get from cityscapes is that it is a really good object detection and a semantic to analyze your semantic segmentation task. That's how you can use these skills. One thing about instance segmentation is, so another thing about instance segmentation is it identifies each object in every instances, and it also tries to differentiate it from its surroundings. And yeah, again, it identifies states and objects in motion. That way, we can perform optical flow estimation like it was done in Kitty.
Everything starts with a problem statement. Oxford first discovered the problem statement. So the problem statement they focused on was long-term autonomous driving. They realized that even though there is data sets, each of the data sets has so much diversity that it might be difficult for them to understand how a single road or a single path which is traveled might change from time to time. So they traveled the same road again and again, which was around the Oxford University, who made this data set, Oxford data set, which was they made about 100 traversals and collected data of 1010.46 kilometer. So this used 4 cameras, 2 2D lidars and 1 3D lidar. Again, revolutionary. Then they also had an extension of the data set. So actually the data set was released in 3 parts. First part was just this, using 4 cameras, 2 2D lidar and 1 3D lidar. The second part was it released a data set using a 360-degree automotive grade imaging radar. Mind you, it is different from the radars which is being used today. It is obviously more expensive. Yes, commercialization is a very difficult process for that. But this radar is also very revolutionary because you can do localization using this radar. The problem with radar today is that the point cloud data which is provided by the radar is very sparse. So you doing object detection on just the radar itself is not possible. But on this radar, it is possible. But of course, we lose information. So over here, when I say Doppler information, you get a lot of information from radar, which is range, azimuth, velocity. You lose all this. But yes, you can do localization, which was very good for them because the task which they identified was localization. So localization and the metric that they used for the metric that they used for defining their task was RMS position, root mean square, and orientation errors. This formula that you see, it is of RMS position. So this metrics are used to minimize the error. So what this will give is, this is the error. The idea is that the error has to be minimum. So this will, so the more the minimum the error is, the predicted bounding box is closer to the ground truth bounding box. The next data set, Waymo. Waymo is a very modern data set. It is still being updated every day. It is.
Please quote your contribution. What you have done. Bit fast. You have only 3 minutes left.
So everything that we're saying is we have gone through the data sets and we're telling our point of view. Like we're saying what they have done, how they have done it.
Yes, you will be having a comparative study table or something.
We have a research gap.
Yes, good.
So, like we have gone through so far, each data set comes up with its own metric on how to evaluate itself against its competitors. Why we are good, why our scores are better. And there is no universal metric for all these data sets. So that's a very huge disadvantage in my opinion, because there's not one single rule which is checking that yes, this is correct or not. If I come up with my own rule saying this is what I believe, and you come up with your own belief that nah, this is wrong, I think this is correct, there will be a lot of clashes. You cannot evaluate what is the right data set. So the need of a universal evaluation metric is necessary for these data sets. That's a very huge research which we found out.
Like I said before, radar is the future, radar is the way to go when we're talking about autonomous navigation. Radar is virtually unaffected by everything. by fog, by rain, by any weather condition, and it can look very far. So there is a very big gap in use of radar in autonomous navigation. Albeit it's coming up, radar is being used every day, leaps and bounds in autonomous navigation with radar. But even now there is a critical gap, critical lack of autonomous navigation data sets which integrate radar into it. So there is a requirement for evaluation, like I mentioned in the first point. So there has to be an evaluation as to how data sets will be representing the driving scenario, because driving scenario, urban complexities, challenging traffic conditions, and the requirements. So if a data set just comes up and says that we are a benchmark, we have done this, we are good, we can't just agree with them. So there has to be a certain amount of guideline, there has to be checkpoints, you have to give them notes that you have to tick that yes, I've done this, and then at the end they'll be able to say that yes, I am a benchmark. So there's a critical need for that as well. That's it.
Detailed presentation, I would say, firstly. My question is, you're saying radar is costly. Yes, radar is costly.
LiDAR is costly, radar is very cheap.
Radar is very cheap, LiDAR is very costly. But you're saying which one is better? LiDAR is better, radar is better?
I will say both of them have their use. The thing is that radar, automotive grade radar, has not been used to a very large degree. LiDAR is very good when you require, say, depth information, localization, you want to do 3D object detection. The radar, on the other hand, is good when you want to use it in all weather conditions. LiDAR is very good for research, radar is very good for deployment or commercialization.
Okay. So, I think both of them are being used now in the testing, all the things. I think Tesla already uses both of them. Huh?
Focuses on camera.
Cameras.
They came up recently, they came up
Why
with
they
LiDAR.
came up with cameras? That is another question.
It's
Because
easy.
It's easy. It's budget friendly.
So, budget friendly
Yeah.
is what I would say. There's also a very big thing that training is very easier when it comes to camera than with sensors.
Right now, we can say that cameras is basically plug and play. We have architectures available, we just push the pictures into it, we have YOLO available. It's very easy to use. A person who does not know AI, who doesn't know anything about even GitHub, can just go onto the page and can just use YOLO. So it is very easy right now.
But that is how the technology should be usable by all.
Yeah, but we're talking about the research community right now.
You are
They are not using radar. That is the problem.
Why they are not using radar? Nobody is wrong. That's what I'm telling you. Okay. Why they are not using radar? Because it cannot be plugged and used for everything. You are talking about the multi-millionaires or the billionaires who can buy it, but the normal people cannot buy it. For them, what will you do? Will you ask them not to use the technology? No. That's where the camera comes in. I get your point. You are saying from research point of view, radar should use radar. Everything should be used. Yes, I get it. But you should here also point it out why they are not using it and why they are using the camera part and why you are proposing.
One thing I would like to point out now. Cameras have been around for 60 years. So there has been enough time to develop technology to make it plug and play. While we are talking about radar, automotive radar hasn't been around for a lot of time. And also, I think it is honestly radar, as long as the technology is being made by the people who are doing research, even that can be made plug and play. Because the people who will be driving the car, they will not be running Europe. They'll just turn on the car and the object detection will happen on its own. So it is being done by the people who are making the car. So that is just one thing I want to point out.
I think this is more on an ideology basis, the usage of the technology. It's okay, from your point of view you are saying, but my only suggestion is when you are going and proposing us something, like you are saying that this benchmarking of the data set should be done, everything well and good. But you are a comparative study. Don't only compare inside the technology, compare outside the technology. That what are the alternatives and why those alternatives should not be used. You getting my point? You are saying this should be used, the data set should be benchmarked for the research, everything should be done. I get your point. But why? Why is a very big question when you compare it to the other technologies. Yes? There must be reason. Put it out that these are the points that they have not considered and these are the points they should consider. It's not about the data set only. It's not only about the data set. It's also about the technology. Can hold it up or not. that much processing can be done at that certain point in that machine or not? Did you point it out? You didn't point it out. You can easily say that yes, it can be done, but still they are not used. Try to put your point that way. Not only the data set has this, data sets like that, or it can be used. And you have to think of everyone, not only the researchers. Yes? Yeah, you're talking about automated movements. Yeah? This autonomous movements. Autonomous movements are what? Are the major part of our daily life and are the R&D companies. Both. So try to have the perception of both, not only one. Okay? Considering everyone is not going to hurt. Yeah. Considering all the possibilities also not. It will make a research. It will make a better research. Yeah. Try to add those points and also try to add something novel from your side. Like you have given a statement, but what is the supporting data to that? There is normally then a comparative study will show. Try to show that okay, this is the comparison and this is why we are saying. Yes? Research facts or showing or proving something that this is why we are saying. Try to add those things. It's a very deep study that you have done. I'm very happy that you have done such deep study. Only part is proving the point, you need to put another point. Yes? Try to develop it. Try to learn and try to propose something of yours also. You are an EC student. Yes? EC students are more hands-on. Yes?
Actually, we were interning at IIT Hyderabad, and we have recently submitted a paper as well as a data set. So the results for that we published that in IEEE on our IEEE conference for robotics and automation (ICRA). So the results of that will come at the January.
See, that would be an add-on to this.
Yeah, that was supposed to be.
That is supposed to be one of them.
Yeah, but like we cannot really talk about it.
Because
It's already
it's
accepted.
submitted.
It's just submit. It's not.
This will come next.
This will come.
So this is the pre-work of that.
Yeah.
That is the advantage.
Yeah.
That is the feature that is there.
That is what we aim a benchmark data set should be.
Yes. Now that point you should see that you should write in the future work will be this. Or this is the thing I'm planning to do. You have to add that. Future work is the last statement that you need in your book. No, good presentation. Very good. Thank you. I guess the next group of real-time duration modification using grain level before extraction. Authors Manikumar, Steve, I request all the presenters for this session to please come. They will be taking a group portion, then continue the session. All the authors. All the authors who have presented now, I request you to come photograph. I repeat, all authors who have presented just now, I request them to come and take a photograph. Are also going to present, can also come.
Hello everyone,
Good afternoon, and this is Manikumar. I am going to present my paper, real-time duration modification frame level epoch extraction, and I am the first author for this paper. And the main objective of this is to get the real-time modification by getting epochs at the level directly on the signal. Okay, I wanted to explain what is duration modification. Duration modification is nothing but changing the length of the speech signal depending upon the required modification factor. And what is the main importance of duration modification? The application of duration modification is duration modification in applications like post-body modification as speech processing and speech synthesis as well. And what is the then what is duration modification? In order to process the speech, we need to adjust the length of the speech signal by changing the duration. So here we will extract the GCA, glottal closure instance, and by using this glottal closure instance, by manipulating this GCA instance, we will do the duration modification. In order to increase the length of the speech signal, we need to add some glottal cycles, or else if we need to decrease the length of the speech signal, we will reduce the glottal cycles. By adding and deleting the glottal cycles, we will modify the duration of the speech signal which we have chosen. And the main objective is we are going to implement this duration modification at real-time applications, and it will be applied by extracting the GCA instance at the frame level. Okay. And these are the following various techniques which have been implemented in duration modification. And the major disadvantage of duration modification techniques are they are applied on entire speech signal, entire complete speech utterance, and they are not applicable for the real-time duration modification techniques. So, and the major disadvantage of this duration modification technique is while doing the duration modification, we will take the speech signal into a frames. Okay, by taking the frame, take the overlapping of the frames. If the overlapping of, after getting the speech signal into frames, we will apply some modification process, and then we will try to concatenate these frames to get the desired duration modified speech signal. Here the challenge arises. By taking the frames, we get some partial glottal cycles at the end of the frame, and starting and ending of the frames, and this is the major disadvantage of these methods which we are using. And while concatenating after the modification process, there might be mismatch at the mismatch at the end of every frame. Due to mismatch, we get the proper duration modification. So here in this here in this proposed paper, for the duration modification, we will get the real-time GCA extraction method. In this real-time GCA extraction method, we no need to require the prior information of the pitch locations. And for extracting the real-time GCS, glottal closure instance, in the speech signal, first of all, we will consider filter which is H of n. And by using this filter, let us consider S of n is the synthetic speech signal. By convolving this S of n and H of n, we will get the XH of n. Means we just consider the synthetic speech signal in order to extract the real-time GCS, and just pass this speech signal to the filter having H of n. This is H of n which is shown in the figure. Then we will get the XH of n, the filtered signal. And first in the figure second, the first column is a representation in the time domain, and the second one is in the frequency domain. And here S1 of n is the signal which got after subtracting after using the local mean subtraction. Here we will use two types of filters. First one we use H of n, which we pass a speech signal and getting the XH of n. And second one is we use the local mean subtraction. Why we use the local mean subtractions? It is in the, suppose if we go to the frequency domain, these are the complete harmonics, and we find the harmonic at the zeroth position. In order to filter this zeroth harmonic at the zeroth position, we will go for the local mean subtraction. Here we will use the 12 milliseconds local mean subtraction value. After this, using local mean subtraction, this is the S1 of n signal which is obtained in the time domain. And here we can observe we cannot find the harmonic at the 0th position. And again this S1 of L, after using the local mean subtraction, we use the H of n filter. By using this filter, again we will get the output XH1 of n. And in the time domain, these values indicates the glottal closure instance GCA instance. It means here in the real-time modification process, we will take some small amount of frames, and by taking this small amount of frames from the speech signal, like example here we consider synthetic speech signal, and doing all this process, we can get the values. Each and every value gets a GCA instance. Here in this real-time GCA extraction process, we doesn't require the previous knowledge of the pitch. By using this GCA locations, we will implement the duration modification process in real-time applications. Like in real-time applications like speech synthesis systems, or else in prosody modification, especially we can use this prosody modification. And in audio processing also we can use GCA, this duration modification. Whatever the glottal closure instance which we can implement the real-time duration modification. See, while processing the speech signal, generally we will take the entire speech signal and we will make it into small chunks like frames. And by taking the small frame, we use to analyze the modification process. Here in the real-time duration modification also, we will take the small frame of the speech signal. Let us consider 32 milliseconds of speech signal. In this 32 milliseconds of speech signal, we will take 20 milliseconds, and the duration modification has been applied. Okay. And what is the main difference between the real-time duration modification technique which we used and the previous techniques is, in the previous techniques they implemented for the entire speech occurrence, and they are not applicable for the real-time process, and they required some prior pitch knowledge, and by concatenating the frames there will be some mismatch and signal to noise ratio. These are all can be avoided by using this real-time duration modification technique. See how the duration modification technique has been done. Okay, duration modification technique is nothing but changing the duration of the signals. Okay, let us consider these are glottal closure instants. Okay, while we are speaking our vocal cord vibrates and we will get the instants, and these are the glottal cycles. Okay, and suppose let us consider beta is duration modification factor. Suppose if I wanted to change the length of the speech signal by multiplying the duration modification factor up to 1.5. Then initially I will detect the 1 millisecond first glottal closure instant as 1 millisecond here, and these are the pitch. These are the glottal closure instants, and this is the pitch period of each and every glottal closure instance. Okay, and first of all we will get in first one, and we will add the difference between the first instant and the first beat and glottal closure instant. We get 6, and this number which is nearer to the glottal closure instance. Okay, so this number is this number which is nearer to the second glottal closure instant. So we will consider the glottal cycles in between these two instants, 6 milliseconds and 14 milliseconds instant, and we will add it into the second place. And again 6 to, and we are adding the glottal cycles in between the 6 milliseconds instant and the 14 millisecond instant. So we will use 8 as a difference pitch period, and we will add for this new glottal closure instant which we got after duration modification, and we will add this, we will get the 14. And again we will check the different the new instant which we got, new value which we got, which is near to the 6 milliseconds or 14 milliseconds. Again it is near to the 14 milliseconds. In this way we will modify the duration of the speech signal without disturbing the pitch periods. Okay, duration modification means increasing the length of the speech signals or else the decreasing of length of the speech signals by preserving the pitch period. This is the main technique which is implemented in duration modification and in real-time process. And the major difference and the major things which we proposed here is all the identified epochs in the region have complete glottal cycles. See, we are having these are the epochs of glottal closure instance, and we are considering the cycles in between each and every epoch. We avoided the partial glottal cycles in this duration modification factor, and this will enhance the concatenation process.
Sir, please go to the results. Okay, conclude.
The proposed method is implemented in the duration can be changed. Here we can implement this real-time duration modification dynamic while changing the speech signal dynamically, and this real-time duration modification can be implemented for the speech synthesis systems like TTS systems and signal processing methods, as well as mainly especially the prosody modification. For each and every speaker, we have their own unique style of prosody. By manipulating the duration, we can use it in prosody modifications also. And this method operates directly on time domain signals, which can be incorporated. The design means whichever the required duration which we want for the speech signals, we can get by operating on the speech signals directly.
Good presentation, sir. My question is that this is an already existing method that you are trying to apply.
This is not the already existing method. The main difference is that whatever the existing methods, we will take the entire speech utterance and we will divide the speech utterance into the frames here. But here we come in the real-time duration modification. They will know the entire speech utterance. It means like in real-time applications which we wanted to manipulate the speech signal. At that time we use this real-time duration modification. And in previous methods,
I'm asking you, what is that you are proposing in this? What is that you have proposed? Can you tell me?
this is the first one in the real-time process, which is implemented for the real-time duration here. This is first one.
For the real-time process.
So the methodology is existing, right? This methodology of whatever you are mentioning, that is existing, right? It has been applied in real time. That's what
Ma'am, means in the existing thing what we have done, the GCA extractions, we will apply for the entire speech utterance which we already have. But here we are using the duration modification in real-time process. Whatever the methods which we used previously, they are not holds good for the real-time applications. Suppose if you wanted to synthesize any systems, like if you want.
some values or parameters for that real time.
The question is, what you manipulation? Is it existing one you are presenting or what is your contribution? See, existing are also real time, but they need entire utterance to modify. For example, we have applications like mouse speaking. We speak to some mouse and it listens to entire utterance and then it modifies some prosody and speaks out. So this is not the method which is proposed. It is not required entire utterance up to 3 seconds. It's very real time. In milliseconds it takes and modifies prosody. That is real time.
Instead of taking the entire utterance, we will take.
The possible applications are, for example, if you want to hide your identity while speaking to others,
Communication has to be done at that point of
that millisecond moment.
on that frame.
And then right.
Basically, definition of the
So real time, the frame size is in milliseconds, 20 milliseconds. Yes, to do and analyze and do modification of prosody. There are many challenges.
Okay, sir. Very good. Thanks. I look at the next presentation. What is the title of the point of interest review summary?
It is not an real time because real time expression of speech if you don't pose an instrument is very serious task. There are many challenges and results are also not promising.
Real-time process, but small functions in milliseconds are required.
2021 ICAS will support same level GCA expect. Global closure
So, good afternoon, guys. So, my topic is on
topic is on points of interest review summarization for help data set in NLP. So this is the basic summarization techniques which we have used in this. Importance of the summarization. So we will have the time to save and also create better experiences and also make informed choices. And coming to data set overview, we are having around 8 million data set. So we are having 8 million of data set, and we have across we are having 5 types of data sets. We have academic data set, business, and also checking, and also review, and tip and user, which we have around 8 million of data sets consist of all these 5 JSON files. And these are the basic NLP things which happen, such as tokenization and parts of speech tagging, and also the sentiment analysis, and also approach for summarizing text pre-processing and automated summarization, and also the human narrative. And coming to the data set, this is a workflow. First we are taking the user input and also the data pre-processing, and after that we are taking the text representation, and after that we are using the NLP task and also model selection, and from that we are going to metrics and fine-tuning optimization, and from that we are getting the summarized output. And these are the evaluation metrics for summarization. So we are getting the extraction ratio and also the row score, and row score is around 0.4%, and also the word overlap. And this is the algorithm which we have used. So results and analysis. So accuracy we have got it around 20% of the, and also the 0.42% of row score. And also coming to the impact of summarization, like we are able to get all the reviews, and also we are able to save the time for the reader, and also helping business and areas for the improvement, and also the limitations and future works. Summarization is still in its early stages. We are thinking to do, like there are very much more to improve. So in the conclusion, future directions, summary. Review summarization using NLP techniques is an effective way. So we are able to analyze the reviews and also the points. And coming to the future directions, we are able to use different type of techniques and also the process analysis. Like we are needing to get more accuracy. So this is regarding the point of interest review summarization using NLP. Thank you.
This is a review that you have done. Okay. So what are the techniques that we have explained?
So we have used DFID, all basic summarization techniques, and VOA, LOI, and last summary techniques.
Okay. Which one did you find for, which data set you have used for?
Help data set.
For the data set, which technique for summarization is giving the best result?
So we have used all of the techniques, and at last we have got last as the question technique.
Which one?
Last
Oh. Oh. And do you know why you know?
When we have tested, we have got that we got around 142 rows. That's the
That's the thing. So when you write something, you should also find, or it should also work fine, but why? Maybe because of the technique, maybe because of the parameters, or what it is.
last is all the POI and LOI combined separate into that. POI means point of interest and LOI means location of interest. So we are just focusing on a single thing, but we are using that last thing, combine all those things into the and we are taking all the
That should be your. Yeah,
so,
that should be.
we are thinking to get more analysis.
text processing and analyzing data. I will not go in for text for sentiment analysis, but larger data set, no, data set is very clear. Take the language data set, this situation might not be there if the such accuracies are coming. Then you will understand which model has what better and how you can use it, how you can leverage it further. Yes. Try to analyze it that way, not only one data set, try to do it for 2 to 3 days. Then you can
Actually, it consists of 8 billion data sets, so actually it's the more thing to do because on our laptop it's not sufficient for that, so we have used separate data.
online. We have always work using CPU.
But actually for coming to the data set, it's actually large data set. We cannot.
It's a large data set, but it's a clean data set.
It's like collab. We can't use collab for that.
But we can always find some. We can use a pre-trained model, make this data set shorter. You can use it smaller data set without creating a bias in the data. You can randomly pick up. You can always do. There's a lot of techniques that you can use with the limited number of resources. Okay.
Thank you.
Try to do that.
Sure, ma'am.
Thank you.
Thank you, ma'am, for patiently listening to all these presentations. Let's meet after lunch at 2 o'clock for the next session. Thank you.